Here we're just going to do a little bit of a screaming overview about databases. What do these things have in common? Something like a grocery store inventory using the ATM, a Google search, library checkout, and so forth. Well, all of these store their data in some form of a database. So you use them all the time. Data are a valuable organizational resource. One of the technologies we use to manage data is a database. And in many cases, a properly designed database is a model of a business, an activity, or some other sort of real world thing. Like their physical counterparts, data models allow you to get answers about the facts that describe the things that it's being modeled. And so in many cases, it's what are we going to do with the data? The questions that need answers that determine what facts need to be stored, what data are we going to store within our database. The shortlift, your sort of classic informatics text, pointed out early on that healthcare organizations figured out that they often didn't have systems in place that allowed them to answer those crucially important questions. And that one of the principal barriers for clinicians is inadequate access to clinical information. So what is a database? Formally, it's defined as a structured collection of logically related data and a description of the data designed to meet some specific information need. So when we think about a structured collection, I like to think about this kind of like a form. There's a slot for every piece of data that you want to store. And you can compare that in some ways to unstructured data like a free text note. We think about the way data are stored in a database like a table or a spreadsheet, sort of in this grid format. And once the data are stored within this grid, then you can sort and organize and manipulate the data in a whole variety of ways. So if we think about a database like storing data from a form, then each copy of the form you would think about as kind of like a row in the table. So the form design is the table, and each copy of it is a row. Formally, we call that a record. And then each of the questions, those get stored in the columns of our database. Those are called fields. Now, most databases have more than one table. In fact, normally it needs multiple tables so that we can avoid storing redundant data. So if we think about the database itself, though, it contains the content, it contains metadata. There are some kinds of metadata that describe the database structures, and there are also metadata often within the system that store things about a particular data item, like when it was last modified or who accessed the record last. And then there's often additional things like rules that help maintain data quality, indexes, and other kinds of structures that help with the performance of the system. Databases evolved as a way to separate the programming applications from the actual data management. They realized that in many cases, multiple applications needed to share data, or they were storing the data redundantly in these separate systems. So the database approach allows this data to be shared and accessible. It also allows the data to be manipulated directly without having to have a specific application connected to it. Well, yes and no. So what we have done is instead we've replaced it with this piece of software called a database management system. And so that is the software that lets us directly access and interact the data, and it manages things like functions that support security and data integrity. This has to do with like how believable are the data. Often also includes things like the ability to recover data if there's a hardware failure. So if you think about database management systems, we're really talking about things like Oracle, Access, SQL Server. In this class, we're going to use SQLite. It's the general software, and then, so you might think about that like Word, and then the specific database might be analogous to a particular document that you created in Word. So why not just use a spreadsheet if we think about this data in tables and rows? In some cases, you actually could if you're careful. And in some cases, a table or a spreadsheet is actually the better answer. But there are some distinct advantages. Among other things, databases enforce rules about the structure of the data and add all those additional functions that help us protect and manage the data. So some of the functions that come with this database approach are things like security systems, integrity systems. Security has to do with who can get into the system and what people can see once they get into the system. Integrity has to do with keeping our data from being modified inappropriately. Concurrency control, that has to do with multiple users. Recovery control, that is like if you have a crash or a power blip, how do you keep from having that corrupt your data? And then what they call a user accessible catalog, that's the description of the data. There's also in the database management system almost always some sort of a mechanism for actually accessing and viewing the data. Now, this may or may not be a graphical thing, and in many cases it could be just a terminal window, but there is usually some way to get in there and actually manipulate directly with the data. Now, one important topic is the idea of views. A view kind of allows every user or certain groups of users to have different windows or perspectives into the overall database. And so you think of a view, it's not a copy of the data, but it's some restricted subset of the overall database. Another fundamental concept that we'll go into in a little more depth later in the class is data modeling. Data modeling is the process of describing the data, the relationships, the constraints, and those constraints are often specific to a particular organization or a particular purpose, use case. Two main purposes of data modeling are facilitating communication about requirements and assisting in understanding the meaning or semantics around the data. So we do modeling for these purposes, and we sort of have this driving question that says, how is this is going to help us decide how are we going to organize our data. Now there's different kinds of models. One has to do with the various architectures like flat files or hierarchical databases. This class is going to focus on relational databases predominantly. And so relational databases, each table stores data about a distinct topic. So a person, place, thing. We call those tables entities. And those are sets of things that have similar properties. We call those properties attributes. And relational databases are built around a set of rules that we now call normalization principles. These are rules for defining the structure, and they help you verify that the data are consistent and that the tables interact according to the principles of relational databases and set theory. So you have multiple tables, and you intentionally have certain columns where the data are shared, where the data are the same in both tables. And that column or set of columns can be multiple columns. That helps us hook the rows up. So that tells us that, for example, the first row of data in the top table matches the first row of data and the bottom row of data both in the staff table. So there are these special columns, these shared data columns that we call key attributes. A special type of a key attribute is a primary key. That is the column or set of columns that uniquely identify a row of data in a table. So every row has to have a primary key, and that cannot be null because then you couldn't find the row. Every primary key has to be unique, and a single primary key. So each table is only allowed one primary key, but that key could be made up of multiple columns. And then corollary to the primary keys are foreign keys, and those are the columns in the secondary table that match the primary key in the original table. And this record matching is called referential integrity. So in this example, the branch number is the primary key for the branch table. The staff number is the primary key for the staff table, and the branch number is the foreign key within the staff table. Well, you can't talk about databases without at least touching on the idea of SQL, the structured query language. That is the programming language we're going to use to communicate with relational databases. It's used to retrieve information, and it lets us really have flexible queries that we design ad hoc. One thing that you'll find about SQL that's different than many programming languages is that it's quasi-English-like. So if I wanted to say, for example, choose the name column from the demographics table, the SQL would be select name from demog, demog being the name of the table. And you can do other things beyond just pulling data back out. You can put data into the table using SQL. You can update the data. You can delete the data. It's also the language that's used to build the tables, assign which columns are the key columns, and do other sorts of data manipulations. And it's used for security commands to create users and give them certain access permissions. That's all done within SQL. We're going to spend a little bit of time walking through step-by-step database design. It really is worthwhile to design the database thoughtfully. Bad design can lead to a whole host of problems, including redundant and inconsistent data. Some of the errors we want to avoid, putting everything all in one table. If you have a complex system, this can often end up with just trash. Other errors, no primary key in your tables. That's a problem because that prevents us from having an ability to link tables. You can have problems if you sort of mix up your logical descriptions and physical descriptions, and we'll walk through the difference between those as we go through the class. A problem that I see really frequently is people put the key columns, those linking columns, they put them in the tables backwards. They put the column in the wrong table. And then there are other sort of issues that can happen through design, and we'll talk through how to avoid some of those as you learn how to do design. I want to point out this is not completely unfamiliar territory. When you do something as simple as even searching Google or PubMed, you're searching a database. And like any database, what you get back is exactly what you ask for. May not be what you thought you were asking for, but they're very literal. It'll return exactly what you asked for. And you've probably figured out in doing like PubMed searches that there are ways that you can structure the search to optimize and actually get back what you intended to look for. Some other things that you'll find is that there are public data sources that using these are great, but they're constrained by their design. And so sometimes you'll get back something different depending on how you ask the question. You have to really ask questions carefully. And then some public data sources restrict you to only asking certain kinds of questions. So there's a public health database called IBIS. I think it's actually IBIS-PH through the health department. But it really restricts. You can't write free-form queries. You can only choose from the options they give you in writing your queries there. And then overall, always a reminder that your query results are only going to be as good as the data that's in the system. So if it's garbage in the database, you're never going to get anything but garbage back out. So when you read articles and they say, oh, they used a database for X or Y, think about what do they actually mean when they say they used a database? What sort of data did they store in it? How is it structured? How is it entered? Who enters the data? Do they understand what they were entering? If they had a linkage between multiple data sources, is that linkage, how well can we rely on their techniques for doing that linkage? So this is sort of a screaming overview. We're going to dive into many of these topics in more detail as we walk through the class.